Welcome to this video on individual random variables. This is one of several videos in a short course on probabilities and random variables posted at terje.civil.ubc.ca, a website that contains notes, examples, and algorithms for structural analysis. Venn diagrams, such as the one shown on this slide, was employed in another video in order to visualize the outcome space for events. Two events E1 and E2 appear in this diagram. The concept of an outcome space extends to random variables. However, for individual random variables, the outcome space is a line. The outcomes, also called realizations, of a discrete random variable occur at specific values along the axis that represents the outcome space. There are many applications for discrete random variables, including the damage states of a structural member after an earthquake. That is because the damage is often categorized into one of several discrete damage states. Conversely, the outcome space for a continuous random variable, shown at the bottom of this slide, has infinitely many possible realizations. The next slide illustrates the concept of a probability distribution for discrete and continuous random variables. For the case of discrete variables, the distribution is referred to as a probability mass function, PMF. It is denoted by a lowercase p if we cover the entire outcome space, then the sum of all probability masses must be 1, in order for the probability never to exceed 1. Similarly, the probability density function, PDF, denoted by lowercase f, for a continuous random variable must integrate to 1 over the entire outcome space. In other words, a PDF whose area is different from unity is an invalid probability distribution. The next slide shows one application for continuous random variables. The figure in the middle suggests the compressive test of a concrete cylinder. This is an experiment that is common in undergraduate education in civil engineering. If we test many cylinders and carry out statistical inference on the results, then we can sketch the probability distributions shown on the left-hand side. Notice that we have measured both the strength and the stiffness in each experiment. Also notice the words aleatory and epistemic, which appear in this figure. Epistemic is a word used to describe uncertainty that can be reduced by additional efforts. Conversely, aleatory uncertainty is inherent and cannot be reduced. Although we do not always model aleatory and epistemic uncertainty separately, we can here imagine that the epistemic uncertainty is reduced the more concrete cylinders we test. Bayesian statistical analysis is particularly strong at modeling the epistemic uncertainty. With only a few cylinders tested, the epistemic uncertainty would be large. If we imagine testing very many cylinders, then the green distribution narrows and converges to the black dashed line. Various sources of uncertainty can be categorized as being either aleatory or epistemic in nature. For example, inherent uncertainty in concrete strength is aleatory. Statistical uncertainty due to lack of data is epistemic. Measurement uncertainty in how the strength and stiffness is measured is aleatory, unless we change the entire test setup. Model uncertainty in a linear elastic structural model is epistemic because we can improve the model by introducing nonlinear finite element analysis. Some argue the philosophical point that all uncertainty is epistemic. One proponent for that viewpoint is the so-called Laplace's demon, which suggests that all uncertainty can be reduced if we just measure and model everything perfectly. Such a viewpoint is unrealistic in engineering. For us, there will always be some uncertainty that cannot be reduced. Another application of continuous random variables is shown on the bottom left side. It is taken from structural reliability analysis, where we calculate the probability that the strength of a structural member, for example, is greater than the applied load. Continuous random variables represent a very important probabilistic model in the short course on structural reliability posted terje.civil.ubc.ca. The right-hand side of this slide plots the strength and stiffness for each experiment as one point. The result for many experiments is a so-called scatter plot, which reveals that there is dependence between the strength and stiffness. If the strength is high for a particular concrete cylinder, then the stiffness is also likely to be high. This is referred to as statistical dependence, of which correlation is one type. It is possible to formulate joint probability distributions to model such phenomena. That is done in another video in this short course, but this particular video is about individual random variables. The next slide highlights an important feature of a PDF. The probability of any specific outcome of a continuous random variable is 0. This may seem paradoxical, but it highlights that the PDF expresses probability density. It is only when we consider a segment of the horizontal axis, for example from x to x plus dx, that we understand what a PDF is. Also notice in the equations on this slide that a random variable is often denoted by an uppercase symbol, while realizations, namely outcomes of the random variable, are denoted by the same lowercase symbol. The next slide highlights that a probability mass function and a probability density function are not the only ways to express a probability function. By summing or integrating along the x-axis, we obtain the cumulative distribution function, CDF. Because the sum of any PMF must be 1, and the integral of any PDF must be 1, the CDF converges towards unity on the right-hand side. Because a CDF is the integral of the PDF is the derivative of the CDF. In other words, the slope of the CDF tells the height of the PDF. On the next slide, we take 1 minus the CDF to obtain what is called the complementary CDF. Notice that the CDF is denoted by capital F and that the CCDF is denoted by capital G. Next, we introduce the concept of statistical moments. Moments are common in structural engineering, and the concept also appears when we work with random variables. We will here work with statistical moments, but let us start with the basic concept of a moment. As illustrated for this cantilevered beam, the moment is force times arm. In this case, the force is F and the arm is L, so the moment is F times L. The moment concept also appears in the analysis of cross-sections of structural members. This slide labels the moment as first order or second order, and as basic or central moments. Consider the first order central moment. Notice that this is an integral along an axis that starts at 0 at the centroid of the cross-section, denoted by the coordinates y0 and z0. That is why this is called a central moment. This integral is called the first moment of area, and it is always 0 when the integration is along an axis that starts at 0 at the centroid. The basic non-central first-order moment is used in order to determine the location of the centroid of a cross-section. Notice for both these integrals that we are integrating or summing a distance multiplied by an area denoted by dA. This product, arm times area, is the reason why we refer to these quantities as moments. Now, let us have a look at the second-order moments. The second central moment is known to structural engineers as the moment of inertia. Notice that this expression extends the interpretation of a moment. That is because we now have arm squared times the area, dA. In other words, this is a second-order moment. The basic non-central second-order moment is used in the parallel axis theorem, which helps us calculate the moment of inertial for cross-sections consisting of several parts. The next slide introduces statistical moments. They follow the same pattern as the cross-section moments. That means we have first and second-order statistical moments that are central or not. Importantly, these moments are partial descriptors of the full probability distribution. When we work with random variables, we often work with partial descriptors instead of the full distribution. For example, we may specify the mean and standard deviation of a random variable instead of the full distribution. On that note, the mean of a random variable is actually the first moment of the distribution, and the standard deviation is the square root of the second central moment, which is the variance of a random variable. Notice that the term moment is used because we integrate arm, namely distance, times probability density. For discrete random variables, the statistical moments are sums of distance times probability mass. Also notice that the word central here means that we integrate along an axis that starts at 0 at the mean. In a sense, the mean of a random variable corresponds to the centroid of a cross-section. This slide also points out the following fact. The mean of a random variable is denoted by the Greek symbol mu and also by the expectation operator, e. The first central moment of a random variable is 0. The second moment is called the mean square. Notice again the use of the expectation operator, which is covered in greater detail in the video on functions of random variables in the structural reliability course. The second central moment is the variance, denoted by sigma squared, where sigma is the standard deviation. The variance can also be denoted by the variance operator or the expectation operator, as shown here. Before we leave this slide, we can explain phrases that appear in structural reliability analysis. One phrase is second moment information, another is second moment methods. From what we have learned on this slide, those phrases imply that we use only partial descriptors of the random variables, instead of the full distribution, and that we include partial descriptors up to the standard deviation, but not higher order moments. This means that second moment methods work with the mean and standard deviation of the variables, and also the correlation coefficient, which is introduced in the video on joint probability distributions. And finally, if you are wondering what the mean square is, one use of it is shown on the next slide. Here, we derive a poem which says that the variance of a random variable is equal to the mean square minus the square of the mean. We start with the expression for the variance, which is the second central moment. Next, we expand the parenthesis that is squared, which gives us three terms, marked in red, blue, and green. The red term is immediately identified as the second moment of a random variable. That moment is called the mean square. Next, we pull the square of the mean outside the integral marked with blue. What remains in the integrand is the PDF. The integral of a valid PDF must be equal to 1, so the blue term is simply the square of the mean. Next, we pull the factor 2 and the mean outside the integral marked with green. What remains in the integrand is x times the PDF. That is the first moment of the distribution, namely the mean. By pulling everything together, we find that the variance of a random variable is equal to the mean square minus the square of the mean. One consequence of this is that the variance is equal to the mean square for a zero mean random variable. On the next slide, we look at a technique that can sometimes be used to calculate the mean of a random variable. This is not about statistical inference using observed data, which is addressed in another video. Rather, this is a situation where we imagine that we have obtained the complementary CDF by some other analysis. This situation occurs in performance-based earthquake engineering, where the probability distribution of monetary loss caused by ground shaking is expressed by a complementary CDF. It is then called a loss curve. Sometimes the concept of occurrence rate is used instead of probability, but the calculation of the mean is the same. Notice that we are here dealing with a random variable whose outcomes cannot be negative. All probability density is on the positive portion of the x-axis. The top of this slide repeats the expression for the mean, namely the first statistical moment. Next, we remember that the PDF is the derivative of the CDF. Because capital G is the complementary CDF, which is 1 minus the CDF, we need this minus sign. Next, we apply integration by parts, which removes the derivative on G and differentiates x once. The boundary term, evaluated at x equals 0 and x equals infinity, vanishes because either x or G is 0. We are left with the integral of the complementary CDF. This means that the mean seismic loss is the area underneath the loss curve. On the next slide, we briefly mention coefficients that are derived directly from the statistical moments. The coefficient of variation, denoted by delta, can be utilized for random variables with non-zero mean. In that case, the coefficient of variation is the standard deviation divided by the absolute value of the mean. This coefficient is used in the following manner. Suppose you have learned that the coefficient of variation of this modulus of elasticity is 10%. What is the standard deviation? The formula shows that the standard deviation is the coefficient of variation times the mean. The standard deviation is here 10% of the mean, namely 21,000 megapascal. The coefficients shown below employ higher order moments. This is less common, so we just mention that the third moment enters the coefficient of skewness and the coefficient of kurtosis is defined in terms of the fourth order statistical moment of the distribution. Many standard probability distribution types exist, both for discrete and continuous random variables. Some discrete distributions appear in the video on discrete stochastic processes, namely occurrence models for events. This slide shows PDFs for a few continuous distribution types. Each distribution has one or more distribution parameters. For example, the normal distribution takes the mean and standard deviation as input. That distribution is shown here for zero mean and two different values of the standard deviation. The log-normal distribution is also common in engineering, and it will be derived shortly. Notice the uniform distribution, which has that name because the PDF is flat. The next slide shows the expression for the PDF for the normal distribution. It is derived from the central limit theorem, which say that the sum of many random variables with different distribution types converges to the normal distribution when the number of variables in the sum is large. When we work with the normal distribution, it is common to reference the concept of a standard normal variable, shown on the next slide. Standard, in this context, means zero mean and unit variance. As a result, the standard deviation is also 1. In this case, the PDF is usually expressed as the lowercase Greek phi symbol, as shown here in blue. The standard normal CDF is denoted by the uppercase phi symbol. The second equation on this slide simply repeats that the CDF is the integral of the PDF. With that notation, we find the value of the PDF and CDF for a realization, x, of a non-standard random variable as shown here in red. We subtract the mean and divide by the standard deviation. Using language from the video on probability transformations in the short course on structural reliability, this is a second moment transformation from a non-standard variable, x, to a standard variable, y. The next slide addresses the log-normal distribution. It turns out that the product of many random variables with various distribution types converges to the log-normal distribution, as shown at the top. By taking the natural logarithm of that equation, we see that it is the central limit theorem that is used also here, because the logarithm of a product is the sum of individual logarithms. This leads to the very definition of the log-normal distribution, namely, if the logarithm of a random variable, x, is normal, then the variable x is by definition log-normal. That means the variable, y, at the bottom of this slide is normal, and the variable x is log-normal. The top of the next slide spells that out. But now we need to use the concept of probability transformations in order to proceed. This is an advanced topic that is covered in the short course on structural reliability. The left-hand side of the equations shown here expresses the applicable probability transformation. The CDFs are set equal, which is equivalent to equating the PDFs multiplied by their respective differentials. By using the notation for the standard normals CDF and PDF, displayed on an earlier slide, we obtain the expressions for the log-normal distribution. Notice the 1 over x that appears in the expression for the log-normal PDF. Also, notice that it is the mean and standard deviation of the normal variable, not the log-normal variable, that appear in these expressions. That is why the next slide is included. Many different symbols are used in the literature, and some of them are here. As is done at the top of this slide, the mean and standard deviation of the underlying normal random variable can be denoted by zeta and sigma. Remember, these are the statistical moments for the normal variable, not the log-normal. With that notation, we consider the table below, which is taken from the random variable document posted at terje.civil.ubc.ca toolbox. Expressions are given for the mean and standard deviation of the log-normal random variable in terms of the mean and standard deviation of the underlying normal random variable, and vice versa. Different computer programs will have different notation and different definitions of the input to the log-normal distribution, so caution must be applied when using this table. The next slide shows the most common application of the log-normal CDF in earthquake engineering. Paradoxically, it is not used as a probability distribution. The application is called fragility functions, which formally are functions that display the failure probability for given ground shaking intensity, here denoted by IM, accounting for uncertainty in both capacity and demand. That definition is a proper fragility function. A similar application of this curve is as the probability of exceeding a damage state for given intensity, again accounting for uncertainty in both capacity and demand. The probability goes from 0 for low intensity to 1 for very high intensity. In short, a fragility function is a monotonously increasing function from 0 to 1. The log-normal CDF is an appealing mathematical function for this purpose because it requires only two input parameters. The notation used in earthquake engineering is introduced by first recognizing that the natural logarithm of the median of a log-normal random variable is equal to the mean of the underlying normal random variable. If we use that fact, then the numerator of the argument to the standard normal CDF written earlier becomes the natural logarithm of x over the median of x. That is shown in the blue equation on this slide. Oftentimes, the standard deviation of the underlying normal random variable, sigma y, is called the dispersion. The blue curve shown here illustrates that function. The point that this is not a probability distribution in this context should be elaborated. Certainly, this is not the CDF for the intensity measure, IM, that appears on the horizontal axis. However, some say that this curve represents the probability distribution of the capacity of the structure or the structural member to resist various intensity values. That is partially fine, with the following two caveats. First, we must change the horizontal axis to be capacity. Second, this will not be a formally proper fragility function that accounts for uncertainty both in capacity and demand, unless the demand uncertainty is addressed in some other way. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.